Last time, we went over a few definitions to get us started on our quest for understanding pre-qualified structures and pre-engineered construction techniques. Today, we're going to go over a few more definitions, and we're going to talk about a concept that I like to call going to ground, which is going to help us think about how stresses and forces work together in a structure and provide us a framework for thinking about how all of those things interplay to help create a safe structure. So first, let's talk about some definitions. Let's talk about members. We're going to use the term member to refer to any structural component or element. And so any structure is made up of multiple members. And we're going to talk about two specific kinds in this course. We're going to talk about columns, which are any members that see an axial load. And often we think about columns as seeing compressive, right? They're used to hold up stuff. But we'll use column to refer to anything that sees both either a compressive or a tensile load. And then we'll talk about beams, which are members that see tangential loads. And later we'll talk about joists and girders or rafter, which are other terms that we can use for different kinds of beams. We won't talk about those today. So the two main members we're going to talk about, their two main structural components, are columns and beams. Now, this raises a big question. Maybe you see it, maybe not. But what about sheet goods, right? Flooring panels, plywood, that kind of thing. They're not columns, obviously, although they might see some compressive forces where something's standing right on top of a piece of plywood that's supported by something underneath. And they're not really beams, right? Because they're really big and they can see tangential stresses in both planes of a sheet of plywood. And anything that sees stresses in both planes or axes like that is technically referred to as a slab. However, the pre-engineered construction techniques used in housing construction and that we typically see on stage in stage construction and that underpin most of the pre-qualified structures that we'll look at actually treats plywood sheets as really fat beams with stresses happening only along one axis. And that simplifies things for us an awful lot in terms of understanding how they work. So while plywood sheets as flooring may look like they resist forces and stresses in multiple directions, we're only going to think about them as resisting in one axis, either the long length or across the width. And we'll deal with them as basically beams, not slabs. The other term we want to talk about is joint. So a joint refers to any point at which two members meet and where forces are transferred from one to the other. The leg on a platform, for example, is a joint. There are two kinds of joints. Fixed joints resist all translation, by which we mean side-to-side movement, and all rotation. So if I have a platform and a leg, the leg can neither move side to side nor twist or rotate, right? Pinned joints resist all translation but offer full rotation. A great example of a pinned joint is the metal legs on a folding table. They spin freely at the axis of their rotation and are only locked in place when the cross member or cross brace is locked into place. So those joints are pinned. They don't move side to side, but they freely rotate. In most construction, particularly the construction that we're going to do in live entertainment, we utilize joints that kind of fall somewhere between the two. They want to resist all rotation. We want them to be fixed, but in reality, they don't resist all rotation. There's always going to be some rotation that happens, even if it's minute. And so for our purposes, we can't really think of them as fixed. So we will instead think of them as fully pinned joints, meaning that they will want to rotate freely. Doing so allows us to basically look at pre-engineered construction techniques from a worst case scenario, that which would be if the joints all rotated freely. If we design assuming that that's going to happen, we will design structures that resist that, and then we're in a safe space, if that makes sense. Why does fixity that's the term we use, the fixity of a joint, whether it's fixed or pinned. Why does that matter? When we think about platforming on stage, it's really easy to focus on the loads that apply forces downward. So booms, scenery, even when we think about actors, we can sort of forget that actors move around. We kind of think of them as stationary, applying a downward force. But we have to consider that there are other forces that are happening, that there are lateral loads that would cause the side-to-side movement of a structure. Dancers don't just move up and down. They move this way, they move that way, and their motions impart lateral forces, which could cause a structure to move this direction, not just resist forces from up and down. If we think about outdoor staging, you got to think about wind and other outside forces. So pre-qualified structures and pre-engineered techniques include cross-bracing requirements that reinforce the fixity of joints to ensure they account for those lateral loads. So we're going to consider all of our joints as being pinned because they are not truly fixed. But in that situation, we still have to deal with the side-to-side motion that could cause loads to move, could cause loads that could cause a structure to move side to side. So to resist that, we add cross-bracing. And all of the pre-qualified structures that we might work with and all of the pre-engineered construction techniques that we'll talk about all include some kind of bracing requirements to resist that. Okay, so those are the key terms, the last key terms that we want to talk about this week to get us started. Let's talk about this idea of going to ground. It seems obvious to say, but safe structures that don't fall down, which is what we want to make, resist all forces acting on them. We talked about that. That's what static equilibrium is. And that's our goal, right, is to make structures that don't fall down, that don't topple side to side. We want structures that resist all of the forces that act on them. No amount of force that we could ever apply will cause the ground below us to move. It resists everything we throw at it. I can't jump high enough or slam something down hard enough to cause the earth to move. It's just not going to happen. We can use that to our advantage. If we design structures such that forces that act on it are transferred from wherever they are applied down the structure to the earth, we can lean on the ground knowing it won't move. However, each structural member in our system will then somehow get squeezed or bent or twisted in some way because there are forces acting on it from outside and then the resistant force of the earth pushing back. If we design it safely, that's what's going to happen. And so those structural members are going to be squeezed in some way and have to resist the stresses that accumulate from that. So let's look at an example, right? Where'd my marker go? Here it is, I think. So we've got this platform, and it is on two legs, and it's sitting on the earth. We've got this 100-pound weight sitting on the middle of this platform. In fact, let's simplify it even more. Let's just consider this as a beam and two columns, right? That 100 pounds is creating a force right here in the middle of this beam. And that beam is sitting on two posts. And so we can imagine that if that weight is exactly in the middle, there's 50 pounds of force pushing down on each column. If that beam isn't moving, and we don't want it to move because we want it to be in static equilibrium, then here, that column is pushing back with 50 pounds of force. Well, when that happens, this beam kind of wants to bend because there's force pushing this way on the ends and force pushing here in the middle. The beam has to resist the tangential stresses that are building up from that interaction between the beam itself and the columns on either end. Let's assume we can build for that. Now we've transferred this 50 pounds of force to each of these columns. So we're now moving this load to the column. The column isn't going to move because it's sitting on the ground. So the column is seeing the earth push against it with 50 pounds of force. The column then is seeing compressive stresses that resist those forces that want it to squish. Does that make sense? So this is what we mean when we talk about going to ground. This 100-pound force is kind of being transferred to here, and then it is being transferred through the column to the ground. When our structures get more complex, when it's not just a beam and two columns, we might have a series of beams and a plywood sheet on top of it. That plywood sheet is going to act like a beam and transfer load to each of the other beams, which are then going to transfer the load to legs or to another beam that supports those. And then that last beam will transfer that load to legs, which go down to the ground. If we can picture where the forces go all the time and how that creates stresses in each individual structural member, assuming the whole unit is in equilibrium, which we want, we can understand how our pre-qualified structures and how our pre-engineered construction techniques work. This didn't really take into account fixity of joints. We were assuming everything up and down. So if we imagine as well that there's a dancer up here now and somehow they are imparting, say, 50 pounds of force that way from a move that they do in that direction, we now have to think about how does this joint, which we're assuming is fully pinned, it's just going to rotate, how does that resist that movement? If it's fully pinned, that 50 pounds is just going to make everything fall down. But we might consider adding a cross brace here and think about how that force then, if this is pinned and this is pinned, but that is also pinned, it's going to not want to really move very much, and how that force is applied here and then down to the floor or the ground. I hope that makes sense. We're going to keep coming back to this idea of going to ground through this entire course, but I think it's a nice framework to help us think about how these pre-qualified structures work and how these pre-engineered construction techniques are intended to work. See you next time.